So, just as a review, when you talk about electromagnetic radiation, and usually we think of this in terms of light we can see red, orange, yellow, green, blue, purple. But this actually extends all the way from radio waves at the long end up to gamma rays at the very short end. And the pattern is, as the wavelength increases, the frequency decreases. And this makes sense if you think of waves on a shore. The farther apart the waves are, the less frequently they hit the shore. Smaller waves that are closer together are going to hit the shore more frequently. And the nice thing about electromagnetic radiation is that in a vacuum, with nothing impeding it, no air or water or anything else impeding it, it has a very constant speed that we've measured to be about 300 million meters per second, or 3 times 10 to the 8th meters per second. And we can use this to set up a ratio, a proportion, to always know if we know the wavelength, we can figure out the frequency, or vice versa. The symbol for wavelength is this lambda, the kind of triangle with the tail looking thing. That's the distance between two same points on any given wave. And we use meters. Frequency looks like a V, but this is actually the Greek letter nu, which is the number of waves per second. And we measure that in hertz, which is 1 over seconds. And speed of light, or of electromagnetic radiation, we give the symbol lowercase c, which would be meters per second. Speed meters per second. So the formula would be wavelength times frequency is speed, or frequency is speed divided by wavelength. The first person to really come up with some idea of what we call quantum theory, remember quantum theory, theories explain things, was a German named Max Planck. And what he discovered was that when things gain energy or lose energy, it's not a continuous slope, it's more like stair steps. They can gain a certain amount or lose a certain amount, but never an in-between. So they could lose what he called a quantum of energy, or 2 quanta of energy, or 12 quanta of energy, but never 1.5, or 12 1/3. And the formula he came up with was the change in energy is equal to some number n, whole number n, times nu, the frequency, times the constant that he figured out. And that's listed on there. Don't memorize that number, it will be given to you. Well, along comes Einstein, who actually was a bit of an interloper here. He took Max Planck's idea and he stole it and said, well, okay, if you can use this to find the amount of energy a light wave gains or loses, well, if light waves are made up of photons, which we know they are, remember that from last year, then, well, this is also the energy of a photon. So energy is h, Planck's constant, times nu, or c over lambda. And then he combined that with his other equation, the famous E equals mc squared equation, to come up with something pretty revolutionary. That matter is, or light and energy is matter, has mass, and mass is energy. They're interchangeable. So if we jump back over the ocean again from the United States, where Einstein eventually ended up, back over to Europe, we got de Broglie, who really grabbed onto this idea that light is both waves and particles. And he said, well, if that works for photons, if light is waves and photons or particles, why can't electrons, which are particles, also be treated like waves? And so he applied this exact same equation, and set of equations, to electrons. And what he discovered was pretty revolutionary. Particles, like electrons, can be described using a wave equation, which, for those of you taking pre-calculus, those are your sines and cosine equations. So lambda, the wavelength, is h over mv. Mv is the momentum, mass times velocity, momentum of the particle. Large particles have very short wavelengths, so it's not practical to treat something as big as a person as a wave, because the wavelengths are too short to even be measurable. But something super tiny like an electron works perfectly. I mentioned earlier that this is a theory to explain something. What they were specifically trying to explain was something called an atomic spectrum of hydrogen. And we looked at this last year in chemistry. When you looked at the spectroscopes at those different burning metals, we saw individual lines instead of the whole rainbow. And the whole rainbow is called a continuous spectrum. The lines are called bright line spectra, not surprisingly. But why? Why would it do that? Why would there be certain frequencies that would be given off consistently every time, but not other frequencies? They figured it had to do something with these very specific quanta of energy. The energy be gained in a certain amount or lost in a certain amount. But why these amounts? Why these specific wavelengths or frequencies? Why these specific energies? What they figured out, and the first person to figure this out we'll come to later, Niels Bohr, was that the electrons were actually jumping between energy levels. So in hydrogen, for example, there's lots of energy levels, 1, 2, 3, 4, 5, and so on. And electrons could jump up, they could be excited up to one of those, or they could then fall and release or emit that energy. And that emitted energy are those bright lines that we see. And depending on how far apart these energy levels are and how strong the nucleus is, that determines the energy of these photon falls and the energy of the light that comes out of there. So when an electron falls, it goes from high energy to low energy. All that excess energy gets released, and it gets released as photons of light, as certain frequencies of light. And since electrons can only be in any one of these levels and not in between the levels, we only see the lights, the bright lines, that correspond exactly to the energies that those electrons lost when they fell those levels. So this was Bohr's model, and this is the one you've seen before, the solar system model, with the nucleus in the center like the sun, the orbits around, and they can go out and then fall back in, and they release electrons. Release photons as the electrons fall back to a lower level. Yeah, it didn't work for anything other than hydrogen. So we needed to figure something else out. Also, it was discovered that electrons don't move in circular orbits. Otherwise, it would have a very strong magnetic presence. Hydrogen would be really magnetic, and it's not. So we know they're not moving in circles. So what we needed was a new model of an atom. It's not plum pudding. It's not Bohr's orbits, like a solar system. It was something new. The electron is a wave. Not a wave that goes anywhere, a wave that just vibrates in place in space. Okay, it doesn't go from point A to point B, it just sits around the atom and vibrates where it is. We can't have half wavelengths because it has to connect up exactly right, and that explains why there's only certain levels that are allowed. Now, these fit into what are called orbitals, not orbits, orbitals. Orbitals are different shapes, and they're really probabilities. This quantum mechanical model is actually nothing more than a really complicated part calculus, part probability, part trigonometric equation that we can solve to find out the probability of finding an electron in a certain area. The area of highest probability is the orbital. The person who really put it all together then was Heisenberg, he and Schrödinger. But the Heisenberg principle, because people don't get this a lot, is that we can know where the electron is really precisely, but not how it's moving. Or we can know the direction it's moving by looking at its magnetic field, but then we can't know where exactly it is. That's the Heisenberg uncertainty principle, and it really only applies to things the size of electrons and smaller. Nothing bigger than that.